I think now I would like to explain about a few tutorial from chapter 3. So the idea of this tutorial is to the usage of Navier-Stokes equation, and then we could solve how to use that equation in a few application here. Okay, so let's say for 3.1. And again, for this tutorial, might be I upload the question, not the PDF notes. So I hope you could make your own notes based on this presentation, and also I will upload this video in my YouTube channel so you could see it and make your own notes. Okay, 3.1. So if we could finish it in 1 hour, I think it's okay. So we don't have to continue this class at night. Is that okay?
Okay, Doctor. Actually, we need
revision also. I haven't finished the revision yet.
Okay. Okay, so I think okay, so we go for problem for chapter 3. So 3.1, reconsider the problem of Coed flow between parallel plates. Okay, as shown in figure 3.1 in your textbook. For a power law non-Newtonian fluid, so we have T tau equal K du dy over n, du dy by the power of n, where n is not equal to 1. So assuming constant pressure and temperature, solve for the velocity distribution, uy here. Okay, so and then between plates, so for n smaller than 1 and n greater than 1, and compare with the Newtonian solution, equation 3.6. So in this tutorial, so we need to prove that the velocity distribution is u is equal capital U over 2, 1 plus y over h. And then we need to determine whether this equation is suitable for all conditions, or we need to do another derivation if the value of n here is not equal to 1. Okay, for Newtonian, we will take the power is equal to 1. So I mean n is equal to 1. Okay, so first we try to prove this one first. So this is the equation of 3.6. So we could first we need to prove the equation. Okay, so from continuity equation, we have this one, du dx plus dv dy plus dw dz. And then this is the Navier-Stokes equation for Cartesian coordinates. And then you know that from that situation, from that condition, we could say that it is a steady flow. So as I said, you need to do revision about the steady flow and also the uniform flow. So we assume that everything about the t is equal to 0. So normally we have a capital D here, du dt. So, and then the gravity is acts vertically. So we assume that rho g will equal to 0 because gravity is not act on horizontal motion. So, and then the pressure along the x is constant. So we have the dp dx equal to 0. And also there is a velocity changes along the direction of y. So mean the du dy here will remain in certain value. So I think by having this one, so we have rho du dt will equal to 0, and the gravity is equal to 0, and the pressure is also equal to 0. And okay, so we have the pressure here, the gravity is 0, and the p is 0, and this is the nabla tau. So the nabla tau here is if you refer back to the my previous note, we could write in terms of mu and du dy. So and then we have this term because we don't have value in z and w, v and w. So we could simplify this one. So we have mu d square u dy square is equal to 0. And then we bring the mu here to the left hand side. So we assume that we could simplify the term is like this. Okay, for this term, please do not assume that mu will be equal to 0. So that is a very wrong interpretation. The idea is 0 is equal mu d square u over dy square. So it means that the multiple of this term must be 0. So then mu is the dynamic viscosity of liquid, and dynamic viscosity cannot be 0. So means that the only condition that could make these two terms equal to 0 is when d square u over dy square equal to 0. Okay, so in mathematics might be we could say that the mu here bring to the left hand side and equal to 0, but in terms of physical meaning, you must know that mu cannot be 0, but the only way to make sure that these multiple terms can be 0 is by having d square u over dy square equal to 0. So that's why we do at this stage. So and then I think I could simplify this one. So we have in quadratic terms of differential term here. So we need to integrate twice. So for the first integration, we have constant C1 here, and then we integrate one more time. So we have this term C1y plus C2. So and then we substitute the boundary condition. So this boundary condition must be based on the diagram given in the question. So for example, we have 2h here. So might be, so this is the 0, and we have plus h and minus h. So we substitute the boundary condition. So at y minus h, so the velocity is 0. Then we could have, okay, so this is the equation that we have, u equal ay plus b. So this is come from here. So I just replace the C1 with A and C2 with B. Okay, that's for me, that's more easier compared to we have C1 and C2. So I just use that one. So we have u equal ay plus b. So and then we substitute the boundary condition. So we have ah is equal to b. So and then we substitute the second boundary condition, and finally we have b equal capital U minus ah. And then we solve this by using these two equations. So we will found that A is equal this one and B is equal this one, and finally we could get U is equal this equation. So means that we could prove this equation is actually similar as the same with the equation that's stated in the textbook as equation 3.6. Okay, but how about the n less than 1 and n greater than 1? So I'm not going to show you that one, so I think you could calculate this one. So I just give you the idea of if n is not equal to 1, you should start your calculation with this equation. So you put the n here is du dn at this stage. Okay, why? Because this is actually the d square u dy square is actually d over dy, and this du dy is actually represent the tau. So this is actually the mu here. We have a mu here. So this is actually the tau. So that's why if you see the first equation here, and we have shear stress, okay, we have the nabla and tau. And the nabla here actually the simplification of process of del y. Okay, and the tau here is mu du dy. So that's why we have mu del square u over del y. Okay, we have del here. Okay, so you must know that the terms of du dy here is actually reflect the value of shear stress, and the first d dy del over del y here is reflect the meaning of nabla. So that's why I hope you can understand this one. So if you want to do the integration for n is not equal to 1. So you need to expand this term and write as d over dy, du dy by the power of n. Why? Because the idea of shear stress for non-Newtonian is k du dy by the power of n. And the k here is actually the dynamic viscosity. So the dynamic viscosity keep changing when the value of n increase. Okay, when the k is actually changing, because if you have n not equal to 1, so your graph is not linear anymore. Okay. So I think you could get this information. This is very common. But to do this one, okay, you just do let the power of n here there, because the value of n is not equal to 1, and then you do the integration as usual, and you found that the value of n will disappear in the middle, and then you will get the same velocity distribution like this one as your final answer. So that's why in the textbook we see this question. Might be this is the third time asking us how about if the n by the power of more than 1 or less than 1, what happened? So the answer is they will show you the same velocity distribution. Okay. Okay, so I hope you could understand this. Okay, and I hope you could do this at your home and prove that for n is not equal to 1, it's still showing the same velocity distribution. Okay, so this is for question number 3.2. So consider the axial Coed flow. So we have the Coed flow here. So with both cylinder moving, so mean we have the idea is we have a cylinder here and we have another outer cylinder here. Okay, and then the fluid will remain at the middle of this one. And however, the both of these cylinder is moved. Okay, I'm sorry, I'm drawing this in vertical. It's actually in horizontal like this. So it means this cylinder moving at certain velocity, and the middle cylinder also moving at certain velocity. So, and I'm not going to plot this one, okay, because it needs for substitute a few data and create graph in Excel. So what I do is just we practice ourselves to find the velocity distribution for this situation. Okay, so because it is involved the circular shape, so we need to start with the we need to choose polar coordinates. So this is the continuity for polar coordinates, and this is the set of Navier-Stokes equation for polar coordinates. So continuity, so it only has one term, so for sure you will use that one if necessary. So in this situation we don't use the continuity equation. So and then for Navier-Stokes equation, so we have three axes. So we have three of them. So one is showing Navier-Stokes in x-axis or r-axis. So and then we have the theta axis. So and then we have the z axis. So the most important things here is you should know which axis that can be used in that situation. So if we see the diagram here, so it is found that this is for sure the axis of R. So and then the theta is the axis which is reflect the rotation of this the motion that rotates like this one, and this is the motion of Z, the Z axis. So and then we must know that with both cylinder moving, so you must evaluate what is the real meaning of that moving, the term moving there. So because if the cylinder rotates at certain speed, it also moves. And if the cylinder move left and right like this, so it also moving. So in this situation, I think according to this velocity distribution like this one, so I take consideration that the motion is actually along the z-axis. So that why we took the z-axis here to start our calculation. Okay, so and then the first step, the rule of thumb is first you need to choose what Navier-Stokes equation that can be used to solve that problem, and the second one is you try to find the easiest way to solve that Navier-Stokes equation. So but the meaning of find a way to solve the easiest way to solve your Navier-Stokes equation means that you need to make a lot of assumption. So for sure, for example, you assume that the flow is steady. That's why the du dz du dt is duz over dt is equal to 0, and then the molecule will flow on the z-axis only. So means that we have a cylinder like this, and the molecule will go only this direction. So it will not moving up, down, and so on and so forth. So the molecule moving up and down. So mean it must have a component in terms of z, in terms of r, and in terms of theta. Okay, if the molecule moves in 3-dimensional. Okay. So means that there are UR. We are not, the molecule is not moving in R direction. So du dz, so means that there are no changes of velocity z in terms of theta. So what this means? So means that if this is our cylinder, so and then the velocity is on z direction. So mean z at this point and z at, okay, I'm sorry, not okay. I'm talking about this one. Okay, so the du dz means velocity z at this point and velocity z at this point is actually the same. So if the same, these two velocity is the same, so mean the du z over d theta, okay, depends on theta here is 0 because there are no changes at all. So and then duz dz is also equal to 0 because the molecule here in z-axis, okay, whether it is here or here or here, the velocity is remain constant. So means there are no changes of duz dz. Okay, and then also the gravity is not act on horizontal motion, and then the density. So here it is not. Okay, this is not, but normally in Coed flow, okay, it will discuss about liquid. So if liquid, we found that the changes of density, we have 0 here is not exist because the density will be constant. So and then we have mu duz dr is exist not equal to 0, and here is 0. I already discussed about this, and I also talk about this. So why duz over dr is carries a value? Because so it means that the changes of uz in terms of r. So mean for sure it has possibility to this molecule and this molecule having okay, so I will draw a new one. So let's say we have this is our cylinder. So this is the axis of R. So means point at this one and this point will show a different velocity. Why? Because, for example, at the middle here, the velocity is very high, and at the end here, the velocity might be slower or equal to 0. So mean there are changes of velocity of uz in terms of r. Okay, so that's why the duz dr here is remain in a value not equal to 0. Okay. So and then so the rho here is not equal to 0, but the value of rho times 0 will give us a 0 value. And then we could do this. So I think we could you could do this. You could simplify this one into this term, and then we know we have 2 times differential form, so we need to integrate it twice. So this is the first integration. So we could get one constant. So and then we integrate for the second time. So we will have this term. So we have C1 ln R plus C2 equal to U, and then we could write as this one. So this is the equal sign. Okay. So we have U in the function of R, means we need to determine the value of U in terms of changes of radius. Okay. So this is, I think you could do this. So and then we could we need to give the boundary condition. So in these boundary conditions, depend on the first situation, we could have at R equal to R naught. So the U will become U naught, and if R is equal to R1, the U is equal to U1. So and then we substitute into the equation, so we could find that the constant is C2. It can be written as this one. Okay, so and then, okay, so we substitute in the equation, so we get this term. Okay, so and then we solve these two equations, so we could finally get the C1 is equal this term, and C2 is equal this term. So we substitute into the common equation here. So and then we could have the UR is equal of this term. Okay, so and then if you want to solve this question, okay, I will not ask this in final or test because you need to do your Excel. So you need to substitute this. This is actually the condition. This is our first condition, second condition, and third condition. But you need to plot this one is actually by make an assumption. So what is assumption? You just make an assumption of value of R. So means that you imagine that let's say this R is okay, this is the 0, 1, and this is might be let's say what 5 centimeters, and the area here is might be 15 centimeters, and you substitute the value. Once you substitute the value, you could plot the graph, and then from the graph you could see the trend of the velocity increment or velocity decrement. So that is the meaning of this question. So that's why I'm not doing the graph plotting.
Doctor.
Yeah.
Can you explain again why we pick z-axis to work on instead of r and theta axis again?
Okay. Okay, we go back to this one. Okay. So first you need to imagine how this thing works. Okay, so we found that if you see to this line, so this will refer the velocity distribution. Okay, I show that we have the UR here. So mean that the direction is like this. Okay, can you get it?
Okay.
Okay, so means that according to this one, so we have the cylinder, the inner cylinder, and this is the outer cylinder. So the cylinder will move. Okay, for example, if we see from the side view, so let's say we have a 2-cylinder here. Okay, so might be the cylinder is moving forward and backward like this, and also this cylinder is also moving forward and backward like this. Okay, because it says both cylinders are moving. Okay, can you get it? And at this stage. Okay, so and then if these two cylinder moving, so means that if we have molecule here, so this molecule will create velocity distribution. So and then because the molecule here have no slip condition, so it will create, okay, if these two, let's say the simple one, so this cylinder is fixed and this cylinder is moving, so it will create the velocity distribution like this one. Okay, means the velocity distribution will become this one. So means that the molecule of fluid will flow or will move at z direction. So if you want to take UR, you want to take Navier-Stokes equation for R exists. So the physical motion must be, okay, because this is an R, the molecule of fluid must move parallel with the R direction. So this motion is not occur. So that's why we cannot take Navier-Stokes equation for R exists.
Which means basically we pick the axis where the fluid move, right?
Yes. Nah.
Okay, okay.
Yeah, first you need to imagine how the fluid move on what axis actually.
Okay, thank you.
Okay. Okay, so then we come to your idea why we don't take the R axis. Okay, for question 3.5, let's say we have the same cylinder. I think this is for the same cylinder. So a circular cylinder or radius R is rotating at steady angular rate omega in an infinite fluid of constant rho and mu. So it is just to simplify our calculation. So we get the question gives us constant P and mu. Assuming purely circular streamline, find the velocity and pressure distribution in the fluid and compare with the flow field of an inviscid potential vortex. So potential vortex is actually what we learned in chapter 1. We learned about ideal flow. We have a linear, source, sink, and vortex. So that is the simple way to determine that one. So this is the way we determine using the Navier-Stokes equation. Okay, so let's say we have a circular cylinder, and then let's say we have another cylinder here, and between these two cylinders that we have liquid. So and then this cylinder might be the center one is rotate at certain speed. Rotate at certain speed omega. So and then assume purely circular streamline. So what is the meaning of purely circular streamline? Means if you have molecule here, so we assume that this molecule will rotate purely in circle shape. So another molecule here will flow at the circular shape too. Means that both all particle will will rotate at its own streamline path. Okay, so it's not cross each other and okay, that is the purely circular streams. Okay, so and then at this situation, we found that we need to analyze this one by using the Navier-Stokes equation in R in theta axis. Okay, I'm sorry. Okay, so because the motion is actually in theta axis, so this is the theta, so the flow is according to this direction. So we take the Navier-Stokes in theta axis. So and then we simplified everything that we could simplify. So for example, we have the u theta over dt is equal to 0. So this is the assumption of steady flow. So means the velocity is not keep changing all the time. So it's steady along the time. So and then the velocity of UR is equal to 0 because there are no component of velocity that move towards the R axis. The gravity is also 0. Okay. So and then the pressure is constant. So we could neglect the value. And then we have U theta UR. Okay. The U theta here, it can be vary according to the R location. So U theta UR has a value, and U theta over D theta. So means that U theta over D theta means we have U theta here over the D theta, along the streamline here. So the velocity will remain constant. So we equal to 0. U theta over dz, so means there are no motion in z. Okay, so and then UR over d theta. So UR means velocity of UR here is equal to 0. So we have the 0 here. But U theta over R square still have value. Okay, please make sure that you understand each parameter, because u theta over dr is not the same with u theta over dr. Okay, we have here. Okay, we have u. Okay, so we don't have. So it means that because it is not in different differential terms, so it is u theta over r square. So we need to remain this term as a valuable term. So and then we could simplify this one. Okay, we could get this term. So and then you know that we have this the by the power of 2 of differential. So we could, so this is means that you need to simplify this term into this one. Okay, so I think if you you expand this term, you could get this one, this term too. Okay, so and then we integrate both sides, so we have this constant. Okay, so and then we integrate again, so we will get this one. Okay, so and then we could have the term of C1 r square over 2 plus C2 equal to UR. So and then we could have this term. So U is this is the velocity distribution, and then we need to find what is C1 and C2. So we need to substitute in the boundary condition. Okay, so maybe I make a mistake in the first explanation. So in boundary condition, if you see, it's give you the R equal to infinity, and the velocity will goes to 0. So in this situation, it's showing that we only have a rotation of one cylinder like this one. Okay, I'm sorry. Okay, so mean we have one cylinder rotate at certain speed. So and then there are borderless here. So all the liquid is here. So we assume that if the R is become larger and larger and larger until one height, until one limit, the velocity will not influence with the rotation of this circle of this cylinder. So mean there will be a molecule where it's not rotate. Okay, so I hope you could understand that. So that's why we put a boundary condition like this one. When R goes to infinity, so the velocity will become 0. So and then here, normally, okay, in mu, for example, in tau, for example, we have tau equal mu du dy. Okay, so here you must know that the u here is linear velocity. So linear velocity means it is in a meter per second units. Okay, and y here is the gap, so the unit is in meter. So however, for rotating device like this one, it's not the velocity is not represent in terms of linear velocity. It represent in rotational speed. So the relation between rotational speed and linear can be shown with this equation. So you have u equal r omega, so which is u here is meter per second, r is the radius, so in so r is in meter, and omega here is in radian per second. Okay, so and then we mean the u equal to 0 here is actually the r omega is equal to 0. So if we substitute this one, so and then we could get the C1 is equal to 0, and then we could get the C2 is equal to r square omega, and then we could write u is equal r square omega over r. Okay, and then so this is the equation. Okay, so and then if you see, okay, if you see tutorial, our tutorial in chapter 1 or chapter 2, we have discussed about the rotating cylinder. They give you a rotating cylinder. They give you the value of r square omega over r and so on. So that is the relation between that question to this one. So this is the way we prove the term of r square omega over r. So, and then to find pressure, we use the R momentum equation. So the R momentum equation, why we use the R momentum? Well, it is because, as I said, you need to understand the nature of flowing, the nature of that fluid. Okay. Okay, to get the velocity, we will take the theta, because in physical, in real condition, molecule will rotate in theta axis. Okay, and then according to our condition, so we are discussing that the velocity is in steady. Steady means the velocity is not changing along the time. So the changing means the velocity on the same streamline, so this is the same streamline, will not change. So mean molecule at here and molecule at here will not it's not changing, it's constant, it's have a same value. Okay, so you know that in Bernoulli equation, when the velocity is constant, so the pressure is constant. So it means it is useless for us to use the theta axis to calculate the pressure, because the velocity changes is zero, means that the pressure gradient is also zero. So, but we have a lot of streamline there, and the pressure, the velocity of here, here, and here is changing, because we declare the highest, the greater the value of r, okay, they will lead to the velocity near to zero. So it means that the velocity at this point and at this point is keep changing. So mean it when the velocity is changing, so for sure there are changes in pressure. So that's why when we want to find the pressure here, we take Navier-Stokes equation in R axis. Okay, so again, so I simplified this one. So we take the R axis Navier-Stokes equation. So we simplified everything. So I think you could understand this one. So and then we could have the term left is rho u square over r equal dp over dr. So here, so this is a very important understanding that you should have. As I said, might be when we cancel each term, okay, we assume that, oh, the density is zero, the mu is zero, and so on and so forth. But actually, you cannot assume that. Okay, as I explained previously, might be the mu is gone, so it is not because the mu is equal to zero. So it shows another meaning. Okay, so here the rho is not equal to zero. That's why we cannot simply says that the value of rho here is equal to zero. Okay, so it carries certain value, so we need to remain this term. So the final term is rho u square over r equal to dp over dr. And then we could rearrange this one. Okay, so and then we could substitute the value of u here, because u here will represent the linear velocity. So we substitute with the rotational velocity. So and then we do the integration, so we could get this value. So and then when you integrate something, so the constant comes out. So and then we need to determine the constant, whether it is equal to zero or not. So the way is we substitute with the value of boundary condition. So here, so because we assume that this is our rotating cylinder, so and then from previous condition, we found that the bigger the value of r, so the velocity will become zero. So r equal r infinity. So the r infinity is the value infinity is not good for this solution. So might be we could assume that, okay, at one point, which is R is equal to capital R, mean the maximum of R. So the pressure here, okay, please alert that we are solve pressure. So please do not give boundary condition reflecting the velocity. If you see the previous calculation, we are determining the equation of velocity. That's why we give boundary condition in terms of velocity. So now we are solving the pressure term. So we give boundary condition in pressure term. So let's say that at certain point, when R is equal to maximum R, so we give as capital R. So the pressure here will equal to pressure atmospheric pressure. So PATM. So normally PATM we will write as P naught. So we substitute here. So P naught at P is equal to P naught at R equal to capital R, mean at certain value of R. So and then we could get the pressure is equal to this one. So this is means first I hope you could understand, not just remember to solve these problems, but you need to understand how you to choose Navier-Stokes equation, the tricks, a few rule of thumb that you should know, and so on and so forth. Because the condition of the terms that you could cancel or not is actually depend on your situation. Okay, so we continue with 3.8. So this is just a very straightforward. So air at 20 degrees Celsius and 1 atm is driven between two parallel plates 1 centimeter apart by an imposed pressure gradient, okay, dpdx, and by the upper plate moving at 20 centimeter per second. So here, okay, I'm not showing you the notes, okay. So because I just I've simplified from the textbook. Okay, the tricks for this question is they give you two parallel plates. So mean the two parallel plates means the motion is the Coed flow, but it gives you another condition which is by an imposed pressure gradient. So the imposed pressure gradient, okay, normally in Coed flow, we assume that the pressure is atmospheric pressure. So by imposed pressure gradient means might be you will have a very close conduit, but you manage to move that two plates. Okay, so this condition is actually the Coed and Poiseuille flow combined flow. Okay, so I just I'm not derive this one. So I think in textbook we just take we could derive the velocity distribution for this situation where the Coed flow still need to count or still need to take pressure difference. So the equation will become like this, okay, from the textbook, and the P here, okay, reflect the total value of pressure, and the equation is like this one. Okay, so means what we need to do is we substitute the value of P into this P, and we could write the equation like this. Okay. So, and then what we need to do is we need to calculate what is dpdx. We need to calculate what is the volume flow rate per unit width if dpdx is equal to minus 0.3 Pascal per meter. So we know that the equation for flow rate is Q is equal to A times V. So in this situation, we have two plates. So it is U times dy, and you know why we use dy here, because we assume that the width is equal to 1. Okay, so another reason that make us let us know that the width is equal to 1 is from the terms of from the term, okay, from the term of the volume flow rate per unit width. So means that all the value is represent by divide them with the width of that plate. Okay, so I think, and then we assume that this is our plate, and the center line is equal to 0, and this is plus h, and this is minus h. Okay, so that's why the limit will minus h and plus h here. So we substitute the value of u that we get previously. So, and then we let the dpdx here in terms of so we let the dpdx as a term. Okay, we don't as a constant here. Okay, because we want to substitute with this value. So, and then we could get this one. Okay, so because here might be you have a problem, so we have another differential here. So, and then we integrate. Okay, so this integration is actually only referred to y only, because the integration is dy. That's why the dpdx here is remain constant. So, and then we have this term. We substitute with the value, and then we could get it is the flow rate is 0.00238 meter cube per second. Okay. So here, normally flow rate Q is meter cube per second. So, but in this situation, they want to we calculate the flow rate per unit width. So mean we already divide with the width. So now the units for flow rate will become meter square per second. So, and then if you want to calculate the dpdx, the pressure which caused the shear stress at the lower plate to be 0. So, and then we depend on the textbook on this. So we could calculate dpdx is equal to 2 mu u over 2h square. So we substitute the value, so we get it is around 0.0728 Pascal per meter. So I think if you check from the textbook, you could get the idea to get this equation.